Okay, so here we got the rest of the question from the previous session. So let's start from question number 6. This is the question written here already. Sec squared x e tan x dx. We try to integrate this. Just remind you, this is C4 core math integration. Right. So that's the function. This is the expression we try to integrate. So here we got two expressions are there, two functions are here. One is sec squared x, other one is e tan x. Two different type of functions, if not expressions, isn't it? They've been times together. Now, since this is e to the tan x, as we know by observation, if you differentiate tan x, you're going to get a sec squared x. You can clearly see the differential of tan x is just in the front of it. So the answer is pretty simple. The answer for this integral would be tan x plus c. That's it. Yeah, this is like unique questions. There are, like I did in the previous clip as well. So in these kind of occasions, we should look into just through observation, see whether we can find the differential of tan x. Whatever power you have here, we got tan x here. If you can find the front, then the integral is straight away that expression there. Okay, so let me write another example for this one. For an example, let's say we had something like this: 2x e to the x squared plus 1. Okay, this is an extra question. Now we can see x squared plus 1. If you differentiate x squared plus 1, we're going to get 2x. You can clearly see that's in the front. So the integral here, the answer would be e, basically that, ex squared plus 1 plus c. That's it. Yeah, it's very useful, very useful. When it's come to e to the e functions like that, they works quite easily. It's an observation method. Okay, right, cool. So let's go to number 7 then. Number 7, ln x, ln x. Now ln x, we try to integrate ln x, just ln x itself. So when you integrate ln x or ln x, we can use something called integration by parts. Integration by parts. There's no other way of there's no other way of actually integrating this. We can do this one. You can write ln x in this format: 1 times ln x. Okay. So there's nothing wrong with that, writing like this, because 1 times ln x against ln x anyway. Now we're going to rewrite this one in a much more conducive format for integration. Okay, so what we're going to do, we're going to write it like this. Now 1 can be integrated, isn't it? If I integrate 1, I'm going to get x. So I'm going to integrate 1, and again I'm going to differentiate it. You see? So basically dx over dx is again 1, right? And I'm going to write ln x as it was before. And obviously I got dx the other side. Dx is basically that dx is written there. Okay. So what I did, I basically integrated 1, so 1 dx basically. I integrated 1, I wrote it there, and again I differentiated it in order to keep the original function, original expression intact. And I just wrote ln x there. Okay, and dx is that dx. Now we can actually, using product rule in a reverse order, I'm not trying to prove it here, a product rule in a reverse order, we can actually integrate this one. So to do that, we're going to do this. We're going to write this as u, the new version of the question. This as u, and this when we integrated from that as v, and write as v. Okay, that is u, that's v basically. Okay. So when integrating, what you're going to do is, it's pretty simple. Now, the answer is this. U times v, basically. Okay. Let me write in terms of u and v, probably it's easy for you guys then. U times v minus is always minus. I'm going to take out that v outside. I would say taking out from the cage. It's like a cage, isn't it? V outside. And I'm going to differentiate u du over dx. Integrate the whole thing. This is called actually integration by parts. So u is ln x, can write ln x. V is x, can write x. Minus v is x minus differentiate the u, which is that, which is outside the cage basically. If you differentiate ln x, what are you going to get? You're going to get 1 over x. Okay, 1 over x. 1 over x dx. They're cancelling out, so you're going to get x ln x minus 1 dx. Again, we can integrate 1 easily. You're going to get x basically. So x ln x minus x plus c. That's the integration by parts. So that's the answer. If you integrate ln x, you're going to get that. If you differentiate this, you will get that. Because the reverse basically. Okay. This can be very useful. I would like to comment on this here. Basically, we integrated 1 and differentiate again. Okay, in order to keep the original expression intact, we didn't violate anything by doing that because we did the reverse again. So reverse. So because we differentiated, we integrated and differentiated. When you integrate 1, you're going to get x. So you differentiate it, you're going to get 1. So there's no changes basically. It's a nice trick, isn't it? And we have not done that to ln x because we can't integrate ln anyway. Right, so we can't, there's no choice of getting ln. Alright. So I think that's basically it. So let me show you another example. You actually, in integrating, in integration by parts, a similar example. Let's say the question was, this is an extra question. Let's say x ln x. X ln x, for an example. We try to integrate. We have 2 different type of functions. Then we know it must be integration by parts. So what we can do here, we're going to integrate x. You're going to get x squared over 2, and again we're going to differentiate it. Okay, so again you're going to get x there, and you can write ln x outside, and the whole thing dx. Okay. Now there are 2 functions called u and v in the new format. This is basically u. That inside that is basically v. It doesn't matter which way around. Alright, so now the answer is basically u times v means x squared over 2 times ln x, or let me write it u times v first. U times v minus is always minus. Minus, take out that guy from the cage. X squared over 2, v basically, that's what I meant. Alright, so basically v and d over dx. So when you're doing this one, practically with this question, u and v u times v would be ln x, ln x times v would be x squared over 2 minus integral v is x squared over 2 du dx would be differential of ln x basically. It's 1 over x dx. Okay, so we're going to get here x squared over 2 ln x minus, they cancel out, so you're going to get x over 2 dx. So x squared over 2 ln x minus, we can integrate this one, you're going to get x squared over 4. Because x squared divided by 2, 2 times 2 is 4 plus c, that's it. Okay, that's basically it. So that's the method of integration by parts. This can be employed in many occasions. Sometimes we can do this one twice to reduce there to something we can integratable. See, now that function is not integratable straight away, but that bit can be integratable, isn't it? That's why it's quite useful. Basically, you're breaking down into something integratable. Okay. Right. So let's go to the next question now. The next one also actually is good. Is also integration by parts. Think ln x squared. Number 8. Ln x squared. Again, we can't integrate ln x squared. So we're going to do the same trick. We're going to rewrite this one as 1 times ln x squared. And I can integrate 1, but I'm going to get x, so I'm going to differentiate it, dx over dx. Write this one beside it, x squared dx. dx is basically from here, right? So we're going to integrate this, we're going to use this one to integrate it. So this is u now, this is u, and this is v. As we know, the integral would look like this, uv minus, always minus, hook sign, integral. Take that guy from the cage, x, v here, and du over dx. Okay? So we got u times v, basically x times ln x squared minus integration. V is basically x, differential of u, that. We're trying to differentiate ln x squared separately. Differentiate that. It's the chain rule, isn't it? So we can differentiate ln x. We can use the chain rule. We're going to get 2 ln x times differential of ln x would be 1 over x. Okay, so that's basically we're going to get to differentiate. So I'm going to rewrite that one there because just the differential of u, basically that. So I can write 2 times ln x times 1 over x dx. Okay, so what I did basically, I've written v there and I differentiated that du over dx, basically differentiated that. And now they're cancelling out. So what I'm going to get, x ln x squared minus 2 ln x dx. Wow. Now we got that something else. We got ln x, integral of ln x. We did in previous question. So we can use that answer to get ln x, because we don't have to do it again, the whole thing. We can, because we know the answer from the previous question. It was x ln x minus x if we integrate ln x, so we can plug the whole that into this. So in the exam situation, You might have to do it again, obviously. But here, because we have done that before, just 2 minutes ago, so I'm just going to use the answer here. 2 times x ln x minus x. See, I integrated that in x in the previous question, so I just use the answer here plus c. Or otherwise, in a normal scenario, normal situation, we had to integrate this again. Using exact same method, integration by parts, and plug the values. So what I'm going to get here basically x ln x squared minus times by 2x ln x plus 2x plus c, that's it. Okay? That's basically. I hope that's make some sort of sense. Let's say if you had 3 there, then you will basically end up getting something squared of ln x here, isn't it? Then you can again do it, you can plug this answer into that, it's just going forever. So integration by parts is integration by part is a method you're reducing the original expression to something doable. You can break it down and you get like small functions or small function, a doable function basically. Okay. So let's keep that answer for a minute because you basically, let me write the answer here. X ln x squared minus 2x ln x plus 2x plus c. Because we might need this answer in the future question in case. So right. So let's look into the next question, number 9. Number 9 is a slightly different one. It's about volume, a volume generation, rotation question. They say the volume integral basically. They say the volume generated by rotating y equals ln x about the x-axis, where x is equals to from 1 to 2. So they are saying find the volume generated by rotating y equals ln x. If you sketch y equals ln x, it will basically look like this, isn't it? That's ln x. Right, ln x. And it basically goes through that. 1. They want us to rotate this one about the x-axis, where x equals 1 to 2. So they want us to rotate, this one like that. You know, like that. So it's going to produce something like a cone, but it's more like, yeah, it's like a cone, isn't it? Like this. So they're asking the volume of this. So since this is rotating about the x-axis, we know the volume integral is given by quite simple equation pi y squared dx. It should be from 1 to 2. So 1 to 2. So let's do this now. Pi, y is equal to, y equals to ln x. Okay, this is basically y equals ln x. You can sub this value into that. Ln x squared dx. Okay. So we try to integrate this is basically the sketch. The sketch is not required, but just for an aid, what we are doing. This is from 1 to 2, isn't it? Ln x squared, integral of ln x squared. We have done the previous question. That's the reason I actually kept that. There you go. That's the volume integral for that. So what we can do, we can just sum it straight away into this. X ln x squared minus 2x ln x plus 2x. Limits are from 1 to 2. So we can plug 2 into that. So and 1 into that, and you can simplify. And plugging 2 into this, basically what I'm going to get 2 ln 2 squared, yeah, minus plugging 2 into that, 2 times 2 is 4 ln 2 plus 2 times 2 is 4. Take away, plugging 1 into that, that's become 1. Ln 1, however, ln 1 is 0. So that's vanishes. That's also vanishes because ln 1 is 0. That's become 2. 1 times 2 is 2. So this become 2 ln 2 square minus 4 ln 2. 4 minus 2 is 2. That's it. That's basically it. If you want, maybe you can rewrite this one in an interesting mode. Maybe you can. What's the common factor here? Common factor is common factor is 2, isn't it? So we can take 2 out. So what are you going to get? Ln 2 squared minus 2 ln 2 plus 1. If you look carefully, we can factorize this. This is not necessary, right? Okay. Now this is fine. This is sufficient. But in case if you want, we can possibly factorize it. We can rewrite this one 2 still outside, and I can write this one as like this: ln 2 minus 1 squared. Yeah. So I can write it like that because I can factorize this one. It's like having x squared. It is like having x squared minus 2x plus 1. How do you factorize it? X minus 1 squared, isn't it? So that's basically it. I mean, that's good enough. If you can just get to that point, it's fine. Sometimes in exam, they can ask you to show that's the answer. So you have to factorize, so if you can simplify. It's always good to simplify to the maximum point. Alright then, so that's it basically. So it's good for the time being. Cool.